Welcome back, Sterile Processing Universe, to the Trust the Process Conference. My name is Bobby Parker with Beyond Clean, and I'm pleased to be hosting this conference for you today. We've got a great session lined up for you, the Sterilization Cycle and Loading Optimization presentation by our friend Dr. Paulo Laranjeira. And Dr. Paulo, he is a subject matter expert in the sterilization process development, validation and qualification, saturated steam, hydrogen peroxide, ethylene oxide in both the pharmaceutical, biomedical, and healthcare areas. His investigations into biological and chemical indicators with different sterile barrier systems have been published in numerous peer-reviewed journals, and I know that we're going to have a great presentation here for you today. Thank you so much for spending your Friday with us, consuming these CEs. And if you're just joining us here in the middle of the day, know that all of these will be made available on demand afterwards. So if you have to step out early or weren't able to catch all of the conference, definitely check back in after the conference has concluded to be able to view all of these on demand. I want to call your attention to just a couple of things on your screen before we get started. The first is the Q&A box over to the side. If you encounter any questions throughout today's conference that you would like to ask, we will always have a Q&A session at the end of these presentations, and try to address those as questions come along. So feel free to interact with us there. Also note the resources section in the corner of your screen, where you will find additional downloadable content related to the conference. And with that, I would like to welcome in our speaker, Dr. Paulo Laranjeira.
Hello, everyone. It's nice to be here with you today. My name is Paulo Laranjeira, and I would like to thank Beyond Clean and for inviting me to be part of this virtual conference, and also 3M for the support. I'm pleased to be part of this the pool of instructors, especially Craig Wallace, which we have been working in many presentations in the past years, and also Ana Castillo Gutierrez, who I had the pleasure to meet recently. I'm a professional sterilization expert. I have been working with any models of sterilization, steam, EO, radiation, hydrogen peroxide, formaldehyde, anything that is related to sterilization, any method I have been working with for the past 25 years, developing cycles, developing process, developing medical device to be sterilized in these methods. And I also did a lot of research and continue to do research, writing peer-review articles. And everything that I find, I always bring to our conferences these new findings. Okay, so today on the sterilization cycle and loading optimization, I'm going to be covering, or the learning objectives are to describe the role of each saturated steam sterilization cycle phase to deliver medical devices that are both sterile and dry. So those are the true requirements that we have. We need to sterilize, and at the end of sterilization, it needs to be dry. And how each phase can be optimized to meet those two goals. Explain the impact of different materials or medical device construction materials, metallic, and I'm calling metallic and non-metallic to prevent saying plastic. So let's go with metallic and non-metallic materials, those medical device and sterile barriers, and see the impact that they bring to the cycle, and identify available resources to optimize the sterilization cycle. Okay? Let's first talk about the principle, the sterilization process, what we have today. So as we know, saturated steam sterilization, is a global chosen method for sterilization. Everywhere we go in the world, especially in hospital settings, the preferred sterilization method is steam sterilization. And the principle is to inactivate viable spores inside of my load. So the sterilization is going to start at a population of 1 million, and during the sterilization process, we'll reach a sterility assurance level of 10 to the minus 6, a possibility of having one viable spore in 1 million that started the process. So when I reach this point of the sterilization cycle, it means that I don't have any viable, or I only have one viable spore. The possibility of having one viable spore is not absolute. So this shows us that the sterilization process is not an absolute process. The product does not come out sterile. It comes out sterilized to a level of one viable spore in 1 million, the initial 1 million. And the sterilization, here have the spores, and the objective is to inactivate the spores that we have inside or on our devices. And at the end of the sterilization, after the whole process, when I open and I remove the cart, my load cannot have water. You cannot have water. What I'm showing here has to be dry. So today we are going to see how we can achieve these two processes by optimizing what we have today. So the sterilization cycle, as all of you know, and this is just going back to the basics to make sure we comprehend, I divide it, and I'm going to divide it in 3 phases: conditioning phase, exposure phase, and drying phase. The conditioning phase, I'm going to remove the air from inside of the chamber, or the inner chamber, and inject the steam to warm up the load. So I have to remove air and warm up the load. Exposure, I'm going to inactivate the spores, and then at the drying phase, I'm going to make sure that my loads are dry. What are our today challenges that we see? We have 2 medical devices over here, right? One medical device is fully metal, another one has a composition of metallic and non-metallic. During the cycle, during the conditioning phase, I'm going to be removing air. So I'm going to be pulling air out of the chamber. I'm going to be injecting steam. So when steam goes inside of the chamber and gets in contact with the medical device at the beginning of the cycle is basically at room temperature. So that device is going to create a temperature difference. It's going to have a temperature difference between the steam and the medical device, and condensation is going to be created. That condensate needs to be removed because I cannot have water in my load. So I do another vacuum pulse. That water, that condensate that was formed because of that temperature difference, right? And a vacuum level is going to evaporate. And since I'm doing vacuum with the vacuum pump, that evaporation is the condensate is going to evaporate and is going to be removed outside of the sterilizer. Then I'm going to eject again another pulse, another steam inside of the chamber. Is going to be warming up that device. So now the temperature difference is not that high. It's getting closer and closer to the sterilization temperature. But I'm still going to have some condensate. So I'll do another vacuum to evaporate the condensate, inject again, and I'm going to be on the third one closer. Then I do another vacuum, remove the condensate, and on the come up, I'm just going to reach the sterilization temperature. At that point, I want my device, my medical device, to have the surface at the same temperature or close to the temperature of the steam that is going inside of the chamber. So for the metallic devices, that temperature is identical on all surface of the instrument. But for that device that has metallic and non-metallic, I'm going to have some areas that when they reach that last phase of the conditioning, going to the sterilization, they're still going to have a higher difference in temperature. And by having that, I will have more condensate formation also. So, on this instrument, close to this instrument, I probably will have not zero condensation, but close to this non-metallic one or the non-metallic part of the instrument, I'm going to have more condensate. And what I just explained to you was what drove my initial research or my willingness and desire to find answers. Why we have so much condensate with non-metallic, with metallic, lumen devices, non-lumen devices. And I started doing research. This is part of one of the studies that I published. So I tried to reproduce and see the condensation and how to improve the cycle. And in this moment, I was only working with the medical device that I had that created a challenge. So we have different lumens here, different sizes with the same length, with a plastic holder, higher height in the end, lower height at the front. And during the research, and I used a lot of chemical indicators in there to understand the behavior of the indicators versus what was going on with the load. I had thermocouples inserted inside of those lumens and outside of the tray. And believe it or not, when I was doing this process, I learned that when we challenge one device, when we only study a device, we are not comparing what we see on our daily hospital practices. When a medical device manufacturer validates their instruction for use, they are using a sterilization cycle that has to be identical to the sterilization cycle that you have in your hospital. They have to use the same parameters. They cannot have specific parameters. We are seeing some extended exposure times. There is a lot of discussion on that. I'm not going to go in there in this presentation. But the point is, when the manufacturer of the medical device validates the instruction for use, they are validating the sterilization cycle using only their load. And even if they try to mimic, it is impossible, to mimic the load that you guys have in hospitals. It is impossible to have or to simulate every single institution load that we have in the US and globally. Therefore, the validation of the instruction for use cannot, and you need to follow the instruction for use, but you cannot say that that instruction for use is going to represent, the same cycle and the same configuration that you have in a hospital. So this is the first point that you need to understand. When you read the instruction for use, that instruction for use is only for that medical device inside of that sterilizer. Is not on a loading configuration like you have in a hospital. So there are going to be differences, and you need to know those differences, and you need to take action to make sure you can deliver those two requirements: sterile, sterilized, and dry. And the manufacturers, they cannot, in their IFU, see whatever, everything that you do in your hospital. That's why the IFU is validated only with that medical device. Then on our side, in a hospital, we have to put that device, and you have to compare the IFUs from the other devices, and then look at what we have and plan the cycle accordingly to make sure everything is going to meet the requirements. Now let's take a look on the sterilization cycle, how the sterilizer controls the cycle. So this is how the cycle, or how the sterilizer controls the cycle, right? And I'm using this drawing. This drawing I did many years ago when I was preparing one of my first presentations. So for those that have been on the market, on the sterilization market, they kind of can relate to this image. These are really old equipment, but the drawing represents exactly what we still have today. And I love to use this drawing because bring back some memory from those times when I was starting my professional life. So the controls, what you see in the sterilizer, right? And also keep in mind that this cycle, the sterilizer, the manufacturer of the sterilizer, when they develop the cycle, they also use simulated weight to determine the mass and how the cycle can be controlled by the equipment, but they do not use your real load. So even the sterilizer manufacturer do not test their equipment with all the cycle configurations that we see in the market. So we need to prepare ourselves and also learn from our process how to better use the equipment. This is how the equipment then is controlled, how the equipment then controls the cycle. We have a temperature sensor that is placed at the drain, and the reason for that is that the steam, when the steam goes, and it can be either steam going through the jacket and then inside of the inner chamber or directly, depends on the manufacturer. But when steam goes inside of the chamber, right, and it's in the gaseous phase, right, and then when it loses temperature, it is going to condensate, and that condensate is heavier than gas and is going to go out through the drain. So the idea is to have the temperature sensor at the coldest spot. So the coldest spot is going to be the drain, because that's where the condensate is going to pass through. That's why the temperature is placed in the drain. The pressure sensor, it doesn't matter, because the pressure measures, because of Dalton's law, it measures the sum of other pressures: air, steam, water, steam. So the pressure sensor doesn't matter where the pressure is. So we can have it on top of the sterilizer, on the side, depends on the manufacturer. And also, we have seen some other manufacturers using additional temperature sensors on the jacket, additional pressure sensors also on the jacket. Okay, but for the purpose of our cycle control and understanding how the cycle can be optimized, we will take into consideration the position of the temperature sensor at the drain. So this sensor at the drain, the temperature that we see from this sensor on the temperature on the indicator is not the temperature that we are seeing on our load. So the theory is that the sensor is placed on the coldest spot of the chamber. That is valid for an empty chamber. In our cases where we have non-metallic we will have situations where non-metallic medical devices or non-metallic barriers, in other words, we will have situations where the temperature inside of the chamber on our product, on our medical device, will be lower than the temperature on the drain. So we cannot consider that temperature that we see on the display of the sterilizer as the temperature that all of my products reach during the sterilization phase, during the exposure phase. That's why it is important to use chemical indicators inside of each package. So today, the sterilizer, the hospital sterilizer that we have today, only allow the end user to change the sterilization temperature, sterilization time, and drying time. So the cycle performance can be measured by the duration of the conditioning and drying phases because the exposure is always going to be the same. And whatever we have beyond a normal cycle is caused on the delays, or the delays are caused by the conditioning phase or the drying phase. Looking to what should be a normal peak performance of a regular sterilizer, let's look into an empty chamber, because with an empty chamber, I remove the variables metallic and non-metallic from the cycle. I would say that we will have, for the conditioning phase, an average duration of 28 minutes. The exposure phase is normally going to be either 3 or 4 minutes, and then the drying phase somewhere around 15 minutes. This will give us about 50 minutes cycle performance. Now, anything beyond 50 minutes is because of our load. And that's where we need to work to maintain the 50 minutes, delivering sterilized loads and dry without extending too much of the time, right? So when we add mass into the chamber, the conditioning phase is going to be longer. And then the worst part on the drying phase is because when we see wet packs, we tend to increase the drying time to solve the problem. So let's divide the phases and let's see how we can optimize what we have today to maintain the cycle around those 50 minutes, which is what I call peak performance of the sterilization cycle. Can vary by manufacturer, but I'm just using an example for the purpose of this presentation. As I already mentioned about the conditioning phase, the first vacuum pulse is normally the longest one because I have a lot of air inside of my chamber, and it takes a little while to remove all the air in there. Then I'm going to inject steam, warm up the medical device, condensation is going to be formed, and here is where we have an extension of the cycle. If I have too much condensate, the longer it will be for me to remove that condensate. Imagine that once I have water or condensate inside of the chamber, in volume, it's 1 to 700. So when a condensate goes from the liquid phase to the vapor phase, the volume it occupies inside of the chamber is from 1 to 700. So it's going to expand, and then the vacuum that I removed air, I will need to pull more because I'm having more air or more steam because I'm evaporating the water, more gas to be removed. That's why you see that the length of the second vacuum is longer because I have in this example, I have a lot of condensate. And as I reduce the condensate formation, I'm going to have shorter and shorter vacuum pulses, the duration. So this is how you see if you're having too much condensate. If the time between vacuum pulses gets too long, is because I have too much condensate. And this is an example of how the condensate, what we are talking about, steam, is going to go inside of the chamber, is going to get in contact with the surface of the medical device. It's going to cool down, and as it cools down, it's going to convert to condensate, and then the vacuum pump is going to remove that water in as condensate and also as gas. So this process is going to take more time if I have more condensate inside of my chamber. All right? So let's look into the critical points for us to have a controlled conditioning phase. First, what does impact my conditioning phase? Air. Steam quality. I need to make sure my steam has the correct quality specified by the standards. I don't have any air leak in my tubing connections around my sterilizer. The condensation caused by metallic or by non-metallic load weight and steam quality. If I have poor steam quality, I will also have a lot of condensation. Then we have, let's look into the load weight. Everybody knows that we have a recommendation of having 25 pounds per package. This is a ergometric recommendation and has been converted also to steam cycle performance on the condensation part of it. So if you maintain the weight around 25 pounds, you're going to be not only looking to your occupational hazards, but also you're going to improve the sterilization cycle. And for 25 pounds, I create 7.7 ounces of condensate. So that condensate, this condensate here, I need to remove during the conditioning phase. Now, for the metallic, it's easy. This is what we have for the metallic. Now, for the non-metallic, we don't have that information. We do not know what is the mass of non-metallics and how much would they create condensate. By not having that reference today, we cannot assume that 25 pounds of metallic will have the same performance as 25 pounds of non-metallic. It's easy to see that 25 pounds of non-metallic will create more condensate than metallic. Therefore, we need to have, and this is something for the standards committee to work on, but we don't have that instruction today. We don't have that added to the IFUs, but we need to do that assessment. We cannot only rely on creating packages because of the ergometric value of 25 pounds, that package is not going to produce condensate. If it has non-metallics in there, and we use the 25 pounds rule, I'm going to have a lot of condensate inside of my load, and I will not be able to have a dry load at the end. So the performance of the conditioning phase, you're going to see it. If you put a 25 pounds of non-metallics, you're going to see that your conditioning phase is stretching because it's creating so much condensate in there that the equipment is not able to remove all of it. Now, let's look into leakage, right? We looked into medical device performance. This is another issue that we have today, leakage. If you go into the technical area or where your equipment is installed, and if you see water underneath your equipment, stop using it. Because if there is water underneath your equipment, there is a high probability chance of air being sent inside of the chamber during the sterilization. And this is because the condensation, when your equipment, you have a steam source that is pressurized, but your equipment is not running, okay? And I have a leakage in my fittings, in a connector, on a tubing, whatever, okay? Steam is going to be coming out because of the temperature difference. It's going to cool down and it's going to create condensate, and I'm going to have water underneath my equipment. When I start the cycle, right, steam is going to start flowing. It's going to have a velocity, a flow of steam towards the sterilizer. So I have a direct flow of steam towards the sterilizer. It's not just sitting there. By doing that, there's the venturi effect. I'm not going to see any more drops or steam coming out, and actually, I'm going to have air being pulled inside of the chamber because of the venturi effect. A gas in speed, flowing through a tube, if I have a crack, is going to pull out air, outside air, inside of the chamber. And you don't see that. You don't see that. The equipment doesn't see that because the temperature sensor is on the drain. This is going to be in the coldest spot inside of your sterilizer, for instance, on your non-metallic devices. Your pressure sensor is not going to measure it because of the Dalton law, because the pressure is the sum of the pressure of the non-condensable gas plus the steam. So the pressure is going to be the same. There is no way you can detect that non-condensable gas that is going inside of the chamber. That's why you cannot use your sterilizer if you have water underneath your sterilizer. The Boyd-Dick test, it's important. You need to do that Boyd-Dick with the cycle, with an empty chamber, to make sure everything is captured inside of that Boyd-Dick, which is going to be the coldest spot inside of the chamber during the test. But that does not guarantee that all air has been detected. The Boyd-Dick has a limit. So you might have a approved Boyd-Dick test, but if you go on your technical area where your sterilizer is installed, and if you see water in there, you're going to have this issue that I'm presenting here. And when we have air inside of the chamber, steam will not be able to get in contact with the medical device. So we're going to have a cold spot. And when I have a cold spot, what happens with steam? It condensates. Then I'm going to have a lot of water inside of my chamber on that specific package or area. All right? All right, now, exposure phase. This is where everything happens related to inactivation of my spores, spore reduction. For us to inactivate our spores, we need to reach this area of the sterilization. And this is today the only cycle phase that is controlled, or that we have standardized requirements. Conditioning phase, drying phase, we don't have temperature variation, pressures, we don't have any requirements for those two phases, the initial and the end. But for the exposure phase, I have specific criteria to say that we have a successful exposure phase. And that's related to temperature, and temperature calculated by the pressure, the measured pressure. So they have to be inside of a temperature band of 3 kelvins during the holding time. So during the whole exposure phase, they would have to be within this sterilization band. And they can differ by one another at 1 Kelvin. And I have to make sure that they hold for that period of time that has been programmed on the sterilizer. So here we are going to have the presence of latent heat. This is the only phase of the sterilizer that latent heat is present. That's why we cannot take into consideration, especially when we are sterilizing medical devices in hospital, the conditioning, the temperature on the conditioning phase or the drying phase. Those temperatures, they do not guarantee latent heat. And what sterilizes our load, what inactivates the spores is the latent heat. So the latent heat is going to occur when we have the temperature variation. So when we condensate, when we have a temperature reduction, that condensation is going to create latent heat, and 80% of the energy used to evaporate the water into steam is going to be transferred to the medical device, inactivating the spores. And this is going to happen many times during the exposure phase until I have reached that 10 to the minus 6, which is the possibility of having one viable spore in the initial population of 1 million. So this exposure phase is fixed. We can extend it. The extension of this exposure phase is normally driven by the type of the medical device that requires more time to reach temperature. It's not going to be within the 60-second range. It's going to require more time for the lowest temperature to reach or to be above the sterilization temperature set point. But as a rule of thumb, this is what we use: 4 minutes or 3 minutes. And that's where we have the inactivation of the spores. The critical points in the exposure phase are related to steam quality. There isn't much we can do on our side when we're preparing the load, but we need to make sure that the steam that is being used has the correct quality. And we need to be sterilizing at the point C where we have here, where we have the highest energy, where my steam is basically 100% gaseous, or 97, which is the standard requirement, 3% water, 97% gas. And as you see, when you reach, so when the cycle, when we are heating up the water, depending on the steam source that you have, if you have a steam source, an external steam source, you're going to receive the steam ready for use, or if you have a steam generator underneath your sterilizer or by your sterilization equipment, is going to do this. It's going to get water, heat up the water to a certain pressure. At that pressure, by holding that pressure, I'm going to have temperature, and I need to heat up that water, that steam, and to move from point B to point C, because this is where the sterilization occurs. So this area, this green area, is where the equipment does not sense if it is in point C or point B, because for the equipment is measuring temperature, and in point B, point C is the same temperature, and the pressure in point B and point C is the same. So the quality of the steam that was delivered to the equipment, or that is being delivered to the equipment, needs to be controlled. The other critical part is related to superheated steam. I am just about to finish data collection related to superheated steam, and I should have that available by the end of the year. And the idea and the evidence that we have is that superheated steam is present in our current, may be present in our current cycles. And if we have this condition, and you cannot see it because, once again, the equipment cannot measure this condition, superheated steam will not allow you to sterilize your load. You're going to have positive BIs or you're going to have spore growth. And the one way to measure is using biological indicators, and the biological indicators will show growth because of the superheated steam. Okay, so to give you an idea of superheated steam, is something related to the dry heat sterilization that we had in the past, ages ago. Dry heat, we don't have latent heat, so we only have dry heat, we only have temperature. And if you recall, it's not you, but people that used dry heat in the past will recall that we needed to have higher temperatures for a longer time to inactivate all the spores. Therefore, if I have superheated steam, I will not be able to inactivate spores in a 4-minute exposure. Okay? All right, now the drying phase. The drying phase is the last phase of the sterilization, and we use the drying phase to dry the load, and it's a phase that allows you to extend the drying. So keep in mind that when you extend, the addition of drying times beyond 15 minutes, even though it is a common practice to mitigate wet packs, it's causing a increase in water consumption if your vacuum pump is water sealed. And normally, every minute that you add to the drying phase, it's going to add, or you're going to consume 2.6 gallons of water per additional minute in the vacuum phase. So it's not only a solution that it's the first solution that you have when you don't know what's going on with that wet pack or why you had that load wet, and you have to increase the drying phase, and you increase the drying phase, and then the package are dry, but that solution, it's also consuming a lot of water, and actually might not be a solution for your cause, because wet packs or these failed cycles, they are not reproducible. It varies by the packaging and the product that I have inside of my chamber. If in the failed cycle I had more non-metallics, and then I have another cycle, then I increase the drying time, then I put another load to test that increased drying time, and in that second load, I do not use the same amount of for non-metallics. Then the load is dry, and I might think that is the solution. The additional time for the additional time added to the drying phase was sufficient, and actually I did not use the same load. And then I have all of a sudden I have wet packs again in the next 2 or 3 days. I see wet packs again, and that's related to the non-metallic loading. So we have to be careful when we extend the time. We really need to do a critical assessment to make sure that's the only solution that we have. And also keep in mind that leakage that I showed you, this is more common than you think. If you have air going inside of your inside your equipment, you're going to have condensate, and that's another configuration that that is not reproducible. You can have more or less condensation caused by that. So we need first to fix all of that, and then come to the drying phase, and then decide what is the optimum drying time. So the drying phase today, there are some manufacturers that allow you not only to extend the time, but also to add a positive pulse. Let's put it that way. This can be either a steam inject or air going into the chamber. I rather use steam, and the reason for that is when you are in vacuum, when you're doing vacuum, right? The temperature conductivity is really bad in vacuum. I do not have temperature transfer in vacuum. It is really hard for temperature to transfer from one device to another. So normally during the drying time, I have my jacket pressurized. It can be about 3%, 5% above what you have in your normal cycle. So the pressure is going to be a little bit higher. So I will have temperature, because of the jacket is all around. I'm going to have that jacket heated up, but that temperature will not reach my condensate in the middle of the chamber because of the temperature conductivity in vacuum. So we need to have that temperature reaching the condensate to evaporate and then the vacuum pump to pull it out. By injecting a positive pulse, I will allow the temperature to reach that condensate inside of the chamber, and then when I do the vacuum again, that condensate is warm enough or has been warmed again, and in vacuum, when I pull it again, the temperature, the pressure of vaporization is going to occur at a lower pressure, and then is going to be removed from my load. So this solution is really a good solution. If you have that optional on your sterilizer, you may use it, but you have to work with your supplier, your equipment manufacturer, to make sure you do the correct configuration. Okay? Now, what you can do is have a loading distribution in a way that that condensate that is formed inside of a chamber close to a metallic device, because at temperature, we pull down the vacuum, right? This temperature on the medical device is still really hot, and the condensate. Remember, the jacket is far away, but because of the medical device, they are so close to the condensate. I will transfer temperature from the medical device to the condensate, and then because I am in vacuum, it is going to evaporate that condensate. So if you have metallic and non-metallic, you have to distribute your load inside or on your loading cart in a way that you have metallics close to non-metallics. It can either be per package, or it can be even per trays. You can have a tray of all metallics, then another one with some non-metallics, and another one with metallics. At the drying phase, when you reach this point down here, where the temperature conductivity is really bad, because of the plastic of the non-metallic being in the middle of the two metallics, the temperature is going to transfer from those metallics to the non-metallic, and is going to help that condensate to evaporate. So that loading, that optimization, how to prepare the loading, take into consideration the metallic and non-metallic, will definitely improve your drying phase. And as I mentioned, the jacket is going to be pressurized 3 to 5% above the chamber, and during the exposure phase, and this also allows or helps during the drying phase. But if this is also added, you will benefit, you will improve your cycle without consuming a lot of water. So for the cycle optimization, what did we see today? Placement of non-metallic close to metallic. If you start doing that, you're going to see a great result if you're seeing a lot of wet packs in your process. Do monitor the weight of your load, every load. Make sure you know what you are placing on your loading carts. And if you have non-metallics, reduce the amount of non-metallics per load, or either per tray or per load. You will improve your cycle. 25 pounds, it is an ergometric requirement, but definitely improves cycle performance. When you add a new medical device, do a new assessment in your loading configuration to make sure that new medical device will be processed correctly and it will not cause wet packs, and it also reach the sterilized condition that you need. I know we do not do temperature mapping, But if you have the opportunity to start using temperature mapping, that will improve your assessment of your load, because by placing thermocouples on the surface of your devices, using a Kapton tape to prevent the temperature going directly on the thermocouple, just by giving the thermocouple the ability to only measure the temperature of the surface, that will greatly improve your assessment. It's going to be a lot easier for you to look into your loading configuration, determine what is the best configuration. And then this is something that I learned. I rather have 2 successful 60-minute cycles than one 90-minute cycle that might fail. I prefer to get a 90-minute cycle and divide it in 2 60 minutes. It might be, oh, we are going to use 120 than 90. Yeah, I know. But those 2 60 minutes that I'm sure are going to be a perfect cycles, I'd rather have 2 perfect ones than one that might fail. Because if it fails, I have to reprocess it, everything again, right? And don't forget, every additional minute to the drying time will increase your water consumption, and it's a natural resource, a scarce natural resource that we have today, and we have to be mindful, right? Okay, so now we reach a point, the fun part, Q&A. So let's go for the question and answers, and I would like to thank you for your time. It was a pleasure being with you in this virtual conference again, and looking forward to a new one in the future. Take care. Thank you. Let's go for the Q&A.
All right. Thanks, Dr. Paulo, for that engaging presentation. Really interesting information that you've provided to us. I'm going to give us just a moment here. I know that Brett was planning on joining us again, and I think we've got to get Dr. Paulo back in. But if you would take a moment and toss a question into the chat, we should be able to get you a couple of questions answered.
Hey, Bobby, can you hear me?
Yeah, I can hear you.
Yeah. Okay,
Thanks for joining us.
Perfect. I had to dial in. I'm having some internet issues. So.
All right. Well, we can hear you. Thanks for joining us.
Sure.
First question that I wanted to pitch your way has to do with water consumption and drying time. Somebody asked, how does drying time increase water consumption for your sterilizers?
Perfect question, and this is normally overseen when we install a sterilizer. We have 2 different vacuum pump systems. The most common one is the water-sealed vacuum pump. So that vacuum pump uses water through the seal to create the vacuum inside of the chamber. So if you have a water-sealed water pump, that pump, when you extend the drying time, you're going to have that pump running more time, consuming more water, and that's why you have the increase in water consumption. There are also other systems, old ones, they use injectors. I don't see those type of pumps anymore that even consumes more water. And there are some newer pumps which are called water-free that uses oil to seal the vacuum. But the most common one is the water-sealed vacuum pump.
Yeah, that makes a lot of sense. I recall in a department that I was working in when we had a water interruption, not only did our washers quit working, but our sterilizers did as well, because you're right, those vacuum pumps run on utility water. And so thanks for that answer. We've got a couple of questions that have come through around load configuration. In your presentation, you talked about metallic and non-metallic items and the way that they're configured. Could you clarify what you mean by those non-metallic packs and metallic packs and how that configuration affects wet loads?
Okay. So as we see the medical device development and the technology that they're moving to using more non-metallic on the medical devices, on the instruments, and also we see some like containers lid that have a non-metallic cover, and I'm calling non-metallic to not use the term plastic. I'm trying to cover all types of non-metallic materials. And the reason, the difference between the metallic and the non-metallic is that the non-metallic does not heat up or does not warm up as metal. They are like they do not absorb heat. So by not absorbing heat, they condensate a lot more than metal. The non-metallic, they are also lighter. So if you look into what we use today as a control measurement, so when we have a person that is looking for reducing wet packs and they try to maximize or try to maintain items to a 25 pounds weight, that's only valid for metallic, because the condensation that the metallic materials make are a lot less than non-metallic. When we have non-metallic, we have a lot more condensate being formed. Therefore, the 25 pounds does not apply. So in this case, what we need to do is to make sure that we have a mixture of metallics and non-metallics, or have non-metallics closer to metallics, so they can benefit from all the absorption of heat that metallics have. So when we are at the drying phase, they are giving temperature to that condensate that was formed that is probably going to be close to the non-metallic. And the only way for that condensate to evaporate is that if we have heat given to that condensate during the drying phase. And non-metallics will not have that heat. So that's why when we are looking to loading configuration, we need to find a way to have, like for instance, if you have 3 trays, one with more plastic, I will have that one in the middle of 2 different trays with metallics. Just to give you an idea how I'm trying to improve the drying phase, try to have that mix of metallics and non-metallics.
That makes a lot of sense. And just from my own colloquial experience, we do end up with more wet packs from those large total joint pans that are in a plastic container instead of in a rigid metal one. And so, that makes a lot of sense about the heat absorption.
That's a perfect example. Yeah, that's a perfect example. Yes. Yep.
Sure. The last question that I wanted to ask, is there, just from a practical standpoint in your experience, an ideal cool down time for a sterilization cycle? Are we overdoing it with the cooling time after processing, or is there, does it just depend on what the item is, on how long it needs to cool after sterilization?
Ooh, that's a good point. So the challenge that we have is related to the IFU from the medical device manufacturers, right? We have to follow what they validated for that device. Unfortunately, they only validate with their device in the sterilizer. They do not validate with a load mimicking the hostel. And because of that, unfortunately, today, every institution needs to determine the correct cool down time for the load configuration that they have for what they are processing. There is not a specific rule of thumb. Right. What I normally try to do is to look into my process, and let's say if I have a 90-minute cycle time, total cycle time, right? I rather work to reduce that 90 minutes to 60 minutes and have 2 cycles. In other words, split the load in a way that instead of running one 90 minutes, I would run 2 60 minutes. That would sound like I'm increasing in 30 minutes, but actually, if I have 2 successful 60-minute runs, it's a lot better than having a 90-minute that might fail. that's something that I try to explain how we should approach the new loading configuration. But there is no rule of thumb. We have to look at what we have and brainstorm about the load and try to find the best cycle configuration.
Yeah, thank you for sharing that. I think if people want to hang on for a little bit longer, we do have time for one or two more questions. Do you have any thoughts on the use of extended cycles? If the true kill time is only 3 to 4 minutes at 270, why do we have these manufacturers with 8, 10, 15-minute exposure times?
Ooh, another excellent question. So this is a challenge that we see on new devices. And once again, we normally see that request when we have either a high-density non-metallic medical device that requires more time to reach the sterilization temperature. If you have the opportunity to use some type of a temperature measurement system, and you have put the thermocouples on those devices, and it can be on the surface, so you can measure and compare the performance, the temperature performance of those devices. You're going to see that the extended exposure time is being asked because those devices, they do not reach the sterilization temperature, 270, 275, at the same time as the other ones. So the medical device that you have a IFU asking for 4 minutes, okay? And if you put that device with the other one that has asked for 7 minutes, and if you have a temperature mapping, you're going to see that the one that is asking for 7 minutes is because it's taking longer for that device to reach the sterilization temperature. That's the reason.
Very interesting.
The temperature performance of the device. Yeah.
And I guess that's not the same across the board based on the design of the devices, and so that's very interesting.
Exactly.
Yeah. Well, thanks so much for hopping on for a Q&A. I wish we had another 10 or 15 minutes to go through these. Lots of questions that aren't going to get answered. If you are one of those people left with an empty bag and a sad heart that your question didn't get asked, you can contact Dr. Paulo directly. You can find him on LinkedIn, but also in the speaker bio section, you'll find contact information if you want to email him directly. I'm sure he'd be happy to continue this conversation with you. And Dr. Paulo, I want to thank you again for that presentation, for sharing with us, and also for coming on for this Q&A time. And listeners, I want to thank you for tuning in again to this session. Our next session will continue after a brief, close to 15-minute break here at the half hour. Thanks so much, and you all have a great day.
Thank you all. Goodbye.